Hello everybody. Today we're going to be talking about the concept of a limit from on two fronts. The first one we're going to explore what it means numerically, and then I'm going to show you a graphical example of a limit and to help us define it. Let's first start out by looking at this rational function f of x equals x squared plus 2x minus 8 all over x minus 2, and what we're going to do is attempt to evaluate a limit as x approaches 2. Now think of a limit as approaching but not quite equaling. Okay, so that's our goal right now. What is the limit of that function as we get close to 2? Well, the idea of dealing with this numerically is pick values that approach 2. So I'm going to pick some values in the x column as we get close to 2. Okay, how about 1.8, 1.9? We will consider 2 for just a minute, 2.0. So I'll just add it to the table just to prove what we're talking about. And then on the other side, we'd have 2.1 and 2.2. Now, what we're going to do is just plug these values in around 2 to the function. Notice if when we plug in 2, we would get an error. You can figure this if you're using a calculator or a graphing calculator and looking at the table of values. But when you plug in 1.8 for the function, we get about 5.8. When we plug in 1.9, we get about 5.9. When we plug in 2.1, we get 6.1. When we plug in 2.2, we get 6.2. So looking at the trend here, we seem to be approaching the number 6, and that is a safe assumption. Now we can drill down even further if we want to. We can go to the hundreds place, the thousandths place, and so forth. But the table will eventually lead us to realize that this limit apparently is 6. Okay, let's look at limits from another perspective. Let's look at a graphical here. Okay, here I have just some arbitrary function. It is a discontinuous function, continuous everywhere except 2 and 4. However, I'm going to show that the limits actually exist on this graph everywhere. Okay, and then to help illustrate this, we're going to evaluate the function at several points, and then we're also going to talk about what the limit is at each of those corresponding points. So we all know how to evaluate a function. What's the y-coordinate when we plug in 1? So when I look over here and plug in 1, it looks like it's about 2.5. So if I were to evaluate this function at 1, approximately 2.5. At 2, we go up, we have an open circle, it's undefined at that point. I'll put no solution, also mean undefined. 4 is interesting. When we go up to 4, we bypass the open circle and go right to the closed dot, which appears to be about 2. So we'll say f of 4 is 2. F of 6, about here, let's call that 1.5. So now we have simply evaluated the function. Now, approaching the limit, taking limits at each of these points, let's talk about what it means. Okay, limit of this function as I approach 1. Well, approach means get near the point in question, but don't quite touch. And in fact, if we were to evaluate this limit graphically, we could see that it approaches the y value of about 2.5. So here the limit and the evaluation equal each other. F of 2. Notice we had undefined, but now we're going to take the limit. And as I approach this value, not equal to it, but as I approach it, it appears to be at 3. The limit here gets close to 3. As I get close to 2 on the x, I get close to 3 on the y-axis. The limit as I approach 4. Okay, same thing down here. Now, for simplicity, we'll just say this approaches 1. Notice the evaluation was at 2, but the limit approaches 1. We get close to 1 on the y as we get close to 4 on the x. Finally, 6. Now 6, the actual value is 1.5. We're going to say the limit, we get close to that too at 1.5. Notice we are approaching this y value 1.5. Notice we can't approach it from the right. There is no definition of the function. Okay, so hopefully this kind of illustrates that evaluating a function and finding the limit really have nothing to do with each other, even though sometimes the values can be the same. So that is two perspectives on limits.